In this video, we'll talk about trigonometric identities and where they come from, kind of their origins and why they are the way they are. Now, by and large, when we talk about these things, you can just use the identity for your work. This video will talk more about where they come from. So if we think about trigonometric functions, a lot of them come from, or they're all derived from the unit circle, and a lot of the identities stem from that idea. So if we look at a unit circle and we allow ourselves to make this angle theta from the x-axis, hypotenuse being 1 because we are on the unit circle, and we have some coordinate x, y. Well, quick recap, we have discussed that if we look at this unit circle, sine of theta is equal to y, cosine of theta is equal to x. Now that's not so much an identity, those are just facts that we know. So if we consider tangent of theta, well, that would be y over x, or if I use strictly sine and cosine, sine of theta over the cosine of theta. Now that's where we would use an identity for tangent. We can, instead of using tangent, rewrite it as sine and cosine as a quotient. Okay? Similar line of thinking if we look at the reciprocals of these. So the reciprocal of tangent is cotangent. I'll do that one first. That would essentially just be the reciprocal of this fraction here with the sine and the cosine. So instead of sine over cosine, it's going to be cosine of theta divided by the sine of theta. And then if we continue with the reciprocal identities, and these ones we've talked about a little bit, if we look at secant of theta, we know that that is the reciprocal of cosine. So this would be 1 over cosine of theta. And if we look at cosecant of theta, that would be the reciprocal of sine. So 1 over the sine of theta. So using these quotients, we can rewrite all trigonometric expressions in terms of sine and cosine, which will come in handy for a future lesson. Now, continuing at this unit circle concept, there is another identity that is very powerful, and it might seem a little weird at first. So the identity is cosine squared of theta, and what this means, the cosine squared, just means cosine of theta times the cosine of theta. So I'm taking cosine of theta and I'm squaring it. I'm taking it times itself. So it'll be cosine squared of theta plus sine squared of theta is always equal to 1. Now that one might seem a little strange, because where does the 1 come from? Why am I squaring instead of not squaring? And again, if we tie it back to this unit circle idea, we make our angle theta, and we think about what these side lengths are. So if we look at the height of this triangle, that would be sine of theta, as we talked about in just a few minutes ago. And then likewise, this would be cosine of theta. Now, if we think about the Pythagorean theorem, if I take the cosine squared, which is this side, and the sine squared, which is this side, that's got to be equal to 1 squared, which is the hypotenuse of my right triangle, which is just 1. So there's your cosine squared, there's your sine squared, and 1 squared is just 1. So there's your 1 squared. That's where that one comes from. This is a very powerful result, and we'll talk about in a little bit how we can use it to simplify trigonometric expressions or even solve trigonometric equations. So these next few identities may not stem so much from the unit circle, they might be more related to the graphs themselves. So for example, if I'm looking at sine of pi over 2 minus theta, we're saying that would be equal to cosine of theta. So if we think about this pi over 2 is in radians, it's also 90 degrees. Now I'm taking to calling these the shift identities because it is technically a horizontal shift. So if we think about the graphs of sine and cosine, sine starts at the origin and then oscillates between 1 and -1, and after 360 degrees it's gone full circle. If we look at cosine, similar kind of thing, except we start at the peak and then we go full circle. Now, you may notice that sine and cosine, if I was to shift them 90 degrees, they would overlap each other perfectly. Sine is at its peak at 90 degrees, or pi over 2 radians. So it makes sense if I shift it to the right, 90 degrees, then I would have a perfect overlap. So sine is just a shifted cosine and vice versa. So very similar identity. Cosine of pi over 2, or 90 degrees, whatever you prefer, minus theta is equal to sine of theta. And that is a very powerful result in that we can turn maybe an uglier sine or cosine expression into a cosine or a sine that's easier to work with. These ones don't pop up very much. It's not so much that you'll use these, but I do want you to be aware of them and where they come from. They do come from more of the graph perspective than they do the unit circle perspective. Now this last couple batches, these ones are pretty useful. They may have other names. I'm taking to call them the symmetry identities. Let's just go ahead and take a look at one and I'll explain where it's coming from. So if we look at sine of negative theta, we're saying this is the same as the negative of sine of positive theta. So if you remember, even symmetry and odd symmetry. So if we look at an even function, this is symmetry to the y-axis, bilateral symmetry. So like x squared is our textbook example. It's a mirror of itself. It folds over the y-axis line. Likewise, odd symmetry that has rotational symmetry. So our textbook example was more of x cubed. It has this point symmetry about the origin. If I was to rotate this right half here, it would spin perfectly back onto itself. So algebraically what this means is that on an odd function, if I plug in a negative value for x, that'd be the same as if I just plugged in the positive and then just made that total negative at the end. So like as an example, if I think about x cubed, I take -2 and I cube it, I get -8. That'd be the same as if I took I took 2, cubed it, and then made it negative after the fact. Two different ways of doing the same thing. It's just this relationship between them. And you may notice that's exactly what we have going on here. Sine is an odd function. It goes to the origin. It has that rotational symmetry. And likewise, if we think about an even function, if I think about f of negative x, that would be the same as f of positive x. So I will illustrate this example in just a second. If we think about x squared, that's our textbook example of an even function. If I was to take -2 squared, well, that's 4. That'd be the same as if I just took 2 and I squared it and I get 4. Because of this symmetry up here. If I pick an x value on the right side, well, that'd be the same as if I go the same distance away, but on the left side, I'm going to go to the same height. I have to in order to maintain the symmetry. Now, where this comes into play, if we consider cosine, cosine of negative theta is equal to just cosine of positive theta. Because of this symmetry, cosine starts at its peak, and then on either side it starts to go down. and then it repeats itself. It has that even symmetry. Therefore, if I pick a positive theta, that'd be the same, or it should be the same height as if I pick a negative theta on the graph. And then last but not least, we have tangent. Tangent is an odd function, so very similar to sine. Tangent of negative theta will be equal to negative tangent of positive theta. So I can think of plugging in the negative theta for tangent, or I can plug in the positive and then just make it negative after the fact, just like I did with x cubed. So just a quick recap. These are all the identities we've discussed in this video, and I know there's a lot, so if you need to pause to write these down, please do. These are facts you can use in your homework. And largely speaking, if I was to highlight a few of them for you, these ones that I've just circled are very, very useful, turning them all to sines and cosines, all the ones that aren't already sine and cosine. Very useful. The Pythagorean identity is very useful. So if you take nothing else from this video, I would take at least these 5 identities. These other ones at the bottom, they're useful. They may come in handy a little bit. It's more I just wanted you to be aware of where they come from. But by and large, this top half are really the important ones. So make sure you write these down, put them in your notes, make sure you have them handy.